dive into the hands-on session, I just wanted to go over what everyone can expect over the course of the week from the hands-on session, and so that we're all on the same page. So, today we're going to basically learn how to use the DACE online toolkit to analyze radial velocity data sets and download radial velocity data sets. So Heather and Nathan are going to go over that online interface, and then we'll also be available to help with any further setup issues after that. Tomorrow we're going to go over a cross-correlation tutorial. Heather's going to go through that and explain how cross-correlation works. This is sort of a fundamental part of radial velocity extraction, at least for modern instruments. And we'll go into a little bit more advanced features of DACE. We'll learn how to use the API, the programming interface, so you can do your analysis in Python if you don't want to work in the online interface. And then from then on out on Tuesday and basically all the rest of Wednesday, we're going to be doing the Planet Hunt Challenge. So we're going to give you a, well, you're going to be able to choose between several different data sets. And we're not going to tell you, these are real RV data sets, but we're not going to tell you which systems you're looking at. And you're going to use the tools that we've talked about on Monday and Tuesday to try to find all the planets in those data sets. And then at the end of the week, so you'll mostly work on that on your own. Of course, we'll be there on Slack for support, and we'll be on the Zoom sessions at the set times that are on the agenda. And then on Friday, we're all going to get together and talk about the results that we came up with. So there's a series of Google Forms that you'll need to fill out. Everyone should fill out at least one of those Google Forms. And we're going to go through those and see how consistent everyone's results were in the planet search. So I think unless there's any questions about logistics or the schedule, we can get started. So are there any questions to start out? Let me open up that panel.
I don't see any in the Q&A for you.
Yeah, okay. So why don't we just get started? Nathan and Heather, you can take it away. Start screen sharing, I suppose.
All right, thanks, BJ. So I'm Heather Segla, transitioning from the University of Geneva to the University of Warwick, and Nathan Hara at the University of Geneva is going to be my partner in crime today to talk you through this. So as BJ mentioned, the plan for today is just to kind of walk you through the basics of DACE. So DACE is the Data and Analysis Center for Exoplanets. It's just an online tool that we found to be particularly useful for running. There's a load of different tutorials that have already been set up by the DACE team, and there's a whole host of public radial velocity data that's hosted on this already. So it's a really nice resource, and as well they link to various catalogs, including the NASA catalog. So go ahead and check out all the various features here. So Nathan has pulled up here on his screen. This is the home page. So you would go to dace.unige.ch, and that will bring you to this main home page. And then because we're interested in the radial velocities and the observations, we go ahead and click on the observation tab. And then that pulls up all the different types of observations that the DACE platform has for exoplanets. So you can see, like, perhaps you want to use this tool to plan your next observing run or something. Maybe you know that you want these particular RVs and you're trying to plan them. You could go here and check that out. Or maybe you want some simultaneous photometry or transit light curves to your radial velocities. They've got a feature to go ahead and check that out as well. But this is the EPRV, so of course we're interested in radial velocities, so we'll go ahead and type our star name into the radial velocity section. So the one that we're going to go over today is 51 Peg. You've heard this one before. This is the Nobel Prize winning planet. So hopefully that will come into play. And today we'll walk you through how you can go ahead and find 51 Peg B for yourself. So Nathan has entered that in, and he went and hit enter, or you return or whatever, and that will load up all the radial velocity data that the DACE platform has for 51 Peg. And you can see here in this right-hand plot where you've got delta RV on the y-axis versus date in Julian date on the x-axis, you have different colors that represent different data sets. So you can see the original LED data in purple, there's some extended LED data in yellow, and a couple other data sets there, including some high-res data from all the way up to 2017. And the reason why we have that delta RV on the y-axis is because the DACE platform automatically adjusts for the offsets. So you can check out what those are by going ahead and clicking on this offset tab, and you'll see that there's these are sort of instrumental offsets for the large part, but sometimes they're offsets perhaps due to stellar variability, which is something we'll touch on Wednesday a bit more why that would be, but primarily they're sort of instrumental offsets. And if you are tacking together different types of instruments, you want to be aware of that. For the DACE platform, we can mostly just trust these, I mean, especially for the ones that we're doing here today, but you may want to go ahead and fine tune those yourselves. But each time we will do a fit with DACE, it will automatically update and fit for these offsets as free parameters. So we can also identify the different types of data sets by going over to this tab where called data selection. So we'll pull that up. And so here you can see the different data sets. And as Nathan pointed out to me earlier today, that sometimes you will see this data set repeated in the sense that like the LED Pub 2004 will contain the other LED data. It was a later publication that included both. And so usually each time there's a publication set out, there's a data set that contains all of that. And if it goes back to the time series one, you can kind of see that by clicking on them. And you can, when you click on them, it kind of flashes up and you can see. And there are times when you zoom in. So what you did there just by clicking and dragging, then you can see that these are actually taken at the exact same time. They have different vertical offsets because they were fit and detrended with a different pipeline. And so to get into the pipeline and how you measure those RVs and would have those different offsets, those are some different tutorials or different workshops that, I mean, different talks that will come up tomorrow. So if Nathan wants to go ahead and show you how to do the zooming. So if he scrolls over on that top bar, you can see the different ways that you can zoom. So you just have you can zoom with a box where you click and drag. You can zoom horizontally, so we'll only zoom in on the horizontal. Probably the click and drag is the most useful. And another thing to keep in mind is for,
sorry to interrupt. I just realized nobody's really watching the Q&A tool. Does someone have a question? Are those instrument offsets pre-calculated and or fixed?
They're fit each time that each time you load the data. So when you load the data, DACE does an automatic fit. And so if you fit, we'll get to fitting a Keplerian. Let's say you have a few different signals in your data and you fit one. Each time DACE fits, it's going to automatically fit for those offsets as free parameters. Would you agree, Nathan?
Yeah. In fact, all the boxes which are ticked in the fit column are fitted every time you click on that button, fit. So if you add other components like a drift to your model and you click on the fit box, then it will be fitted as well.
And if you want to hold it fixed, you can just unclick the fit, and you can manually adjust that. So if you had a particular reason that you wanted to hold it fixed, perhaps you were trying to repeat the analysis of someone else, and they said that there was an instrumental offset of X, you could go ahead and fit that in and double check and see if you can get their results. Any other questions at this stage?
No, that's it for now.
Okay, thanks very much, Don. And please feel free to jump in anytime you see something. So another useful feature is this sort of import-export on the top right-hand side of these plots. So if you get your plot to a state that you really like, you can actually go ahead and you can export the plot itself. And you can also export the model Keplerian that you fit as well. There's a variety of different things that you can go ahead and export. And say in the future, you're using this tool for your own radial velocity data, you can actually import your own data as well. So if you're working on some private data, you could go ahead and do that as well. So then the next thing I want to mention is that sometimes you might have outliers in your data, or you might want to just see if one particular data point is impacting things more than it should. So if Nathan goes ahead and clicks on any one of these points, you can see there's a whole lot of different displays. So you could decide that you want to download just the cross correlation function, or the 1D or 2D spectrum for this, or the FITS header. There's a variety of different things you could download it and really get into the guts and inspect those. But most likely what you'll be using for the tutorials that we're going through is to be able to remove a point. Sometimes you might have an outlier, perhaps from a cosmic ray or something. You can go ahead and you can just kick that point out if you want. All right, and then if we scroll down a little bit, we'll see the periodogram. So DACE will automatically compute a periodogram. And if Nathan goes ahead and clicks on the peak of that periodogram, you can see all the different information that you can get from that. And he'll show you he'll walk you through now how we can use this periodogram to identify signals and to fit them out and start pulling out some physics.
And Heather, first of all, I've deleted a data point, but I had no good reason to do it. So I'll go to data selection and I'll click on reload deleted points. So now if I go back to time series, I can see that the point that I've deleted is now back on. Okay, now let's look at
Heather and Nathan, we have a question from the Q&A, if I can interject here real quick. I think it's a fundamental question about where DACE gets its data from. So is it from an archive somewhere, or is this data that was input by the Geneva team and they only have access to it? Where is the data coming from?
Several sources actually. So you have you can manually put the data in the database. So we check for new data regularly, and also I think some of the data is automatically imported.
Yeah. So for example, any sort of data that is native to a Geneva pipeline, perhaps like the HARPS data, once that becomes public, that will go on here. And if it's not on here, it's just because they're still in the process of building up everything. And if there's public data that you want on here, you could go ahead and ask the DACE team to include it. But for the most part, they've sort of scoured the different public archives that they have and are working to sort of consolidate all of them. But a lot of the data that you will see is HARPS or LED or Corley, because these were native to originally Geneva, and so they were the easiest ones to import from the beginning. But you'll notice, like how we have here with 51 Peg, there's some high-res data as well. So there's often high-res data, and so but it's all public data. And like Nathan said, you can upload your own private data as well, which you would do if you create an account, which you can see in the top right-hand side, but you don't have to create an account. You don't have to create an account to import things or not, but if you wanted to import perhaps private data or something, you might want to have an account for something, but you don't need one for any of the things that we're going to do for this workshop.
Yeah, exactly.
And maybe perhaps before we jump into the periodogram, we can go ahead and we can look at the correlations tab, just to kind of make sure that you know that it's here. It's not something that we will really need to go through today, but there might be various stellar variability indicators that we'll dive into more on in Wednesday's talks about where they physically originate and what they mean. But this correlation tab is a way to look at radial velocity versus some other type of indicator. Okay, so are there any more questions before we jump into the periodograms?
Yeah, so can you elaborate on how private data are handled, Nathan? Do you know how are they kept secure? In other words, should people be worried about uploading confidential data? My OSB, yes, but
I know that it's not saved anywhere in Geneva.
okay.
Like when you upload the data, we don't have any access to it. Yeah. So you can safely upload confidential data. At no point, nobody in Geneva will know about this.
Okay, thank you.
You're welcome. Okay. If you're interested in stellar activity and how you can handle it with DACE, you can also look at the tutorial number 3, which is on the YouTube channel of the Sagan workshop. Okay, so one more thing also before diving into the parallelogram, I'm going to unselect some of the data sets because as Heather said before, these are the same raw data, but with different processing software. So, but when you analyze the RV, you don't want to have 2 times the same data. I'm going to apply. And then I click on apply data selection. Okay. Now for the periodogram, if you are not familiar with what a periodogram is, I think a few talks will clarify this in the future, including mine. So basically you are looking at you select one period and you look at how well you would fit the data with a sinusoidal component at that period. And so if you have a peak in the periodogram, it means that at this particular period, you have a very good fit of a sinusoidal at that period and the data. And here you can see that you have one peak here at 4.2 days, which is the known period of 51 peg, but you have also peaks at 1.3 and 0.8. In fact, those are aliases. I mentioned it in the tutorial on the channel. You can spot those by clicking on the peak and then click on add aliases. And this will show you the position of the alias if you have a periodic component at this period. Like so it means if you have a periodic component there, you will also have signals there and there. And I click on this icon to clean the periodogram. What I can do also is to switch between period and frequency. Here, the periodogram is plotted as a function of period, but I can plot it as a function of frequency. And so in particular for the aliasing problem, this is very useful. And something I didn't talk about in my previous tutorials is the notion of spectral window, which will help you understand further the notion of alias. So the spectral window is displayed here in days. And for you to understand what it is, I'm going to click on the main peak and on align PSDW, so power spectral window. And you see that it looks very similar. And why does it look similar? In fact, the spectral window tells you that if you have a signal at this frequency, a pure sinusoidal signal, like no noise whatsoever, then this is the periodogram that you would get. And you see that it's very, very similar to the periodogram that you get here. So in fact, you could say that already you can see that the signal is very close to just one sinusoidal component plus white noise, because in the periodogram of the data, you have a little bit more power spread in the periodogram, and this is a little bit cleaner. Okay. Second thing you can look at is the log 10 FAP, the fourth row starting from the top. And log 10 FAP is for log 10 of the false alarm probability. And the false alarm probability quantifies whether this peak is compatible with the noise or not. And the lowest it is, the higher is your confidence that you have detected something that it is not due to noise. So here, the log 10 is below -16, which means that the FAP is below 10 to the -16. It's very low, so that is a very clear signal. So I'm going to click on this peak and then on add Keplerian. Now, I have another field. I have 5 other fields here, which are
And just to jump in here, in case someone missed it, it was a little bit subtle. He clicked add Keplerian and then he went back and hit fit. So just make sure that once you add your Keplerian, you refit your data, and then it's going to fit those offsets with that Keplerian as well.
Yep. And so before we comment on these, I just want to make one point, which is that you see that in the residuals, here I have a peak at log 10 fap -7, and here it's -8. And these are significant signals. And you can see that the highest peak in the parallelogram here is close to 1 day. And whenever you see something significant at 1 day or at low frequency, but like here in that case at 1 day, you might expect that it comes from an instrumental feature. And in the first part of the tutorial, I went into a little more details about that, identifying where this comes from by selecting individually each instrument and recomputing the parallelogram on each instrument individually. But here we are not going to talk about that into more details, and I think Heather will tell you about the orbital elements.
We have a couple questions that maybe now would be a good time to address.
Sure.
So why do alias peaks show up when you get a real signal? It's kind of deep question, but you could take a short stab at it maybe. Why do you see aliases in the periodogram in the presence of a real signal?
I think one way to look at it is that the sampling in the radial velocity is almost regular. It's almost 1 day. And if your sampling was perfectly regular, then you would you would have several periods which would fit exactly the data. I'll talk about it into more detail in my talk. I think it's kind of hard to see without a figure. But,
yeah, I agree.
Yeah,
basically how you can fit a sine wave through points, and if you sample at 6 points, then you can you can be confused by the true period.
Maybe I have an answer to your question. So here, going back to the time series, I can click on phase folding. And here, the data is phase folded at the period of the planet, and you see that the data, the model explains very well the data, right? Now, if I delete the Keplerian signal, I'm back to my original parallelogram of my original data. But what if I add a Keplerian on the alias? Then I do not get rid of all the power there. But when I go to the phase folding, you see that it still works somehow. Like you can still explain a little bit of the data with that period. So aliases are a particular instance of a much wider situation where you have two models, two sets of parameters in your model that can explain fairly well your data. And so you have like a fundamental uncertainty on whether it's one set of parameters or the other. Yeah.
Okay. What type of periodogram is this? Is it Lomskargel or generalized Lomskargel?
It's a bit more elaborate. It's a kind of generalized Lomskargel periodogram, because in the generalized Lomskargel periodogram, you fit a constant function at any trial frequency. You fit a constant function, and here at any frequency in the periodogram, you refit also all the offsets and all the drift, and if you add some detrending with the activity, it is fitted also. Like the only thing that it doesn't refit at each frequency is the parameters of the planetary system. And this is covered in the part 4 of the tutorial, if you want like the mathematical details about it.
Yeah, and we've mentioned these tutorials, but I guess it's probably good to remind everyone, if you haven't looked at the website so carefully, Nathan has done a phenomenal job putting together 4 different concise tutorials going through these days things. So if there's something today that you've kind of have forgotten about, there's a cheat sheet, and we'll show you where to pull that up before we sign off. And we'll also show you where to go ahead and find those tutorials. They're on there, and they're usually about 10 minutes or so, I think. So go ahead and make sure you check out the various tutorials that he put through. They're really good. Nathan, maybe you want to mention a little bit more about, someone I saw asked about that one day. How does it relate to the instrument, I guess? Can you talk a little bit more on why you might suspect why you might find a 1 day period suspicious?
Well, you have several effects at 1 day, like several systematic effects in your instrument that can happen at 1 day. And I'm not sure in this panel I'm the most qualified to talk about them, but like you have the temperature, which follows a sort of periodic pattern, and which affects all your measurements with this particular periodic pattern. But you can think of many other effects that affect your data with a period of 1 day. And my experience is that with all the instruments, especially old data, it is not uncommon to find a signal here at 1 day.
So it's largely related to correlated instrumental noise, right?
Probably, yeah. And another effect that might happen is that you might have signal at low frequencies, and the aliases of low frequencies are close to 1 day.
And if there's anyone else, any of the other panelists here that have anything you want to add to that, feel free to jump in.
I would say that the aliasing is the most common thing, that when you have low frequency power, you can't distinguish between low frequency power and power that occurs during the day when you can't observe. Yeah. And so it'll always show up right there at one sidereal day.
But I must say that sometimes you correct, like here, for example, you can detrend you can add a linear trend to your data, and I'm not sure, I haven't done it, but yeah, it kills the power at low frequency, but you still have power around 1 day. So I believe that to some extent, the signal is real and comes from the instrument.
I agree.
Yeah, in this context, it's also worth watching out for periods that are exactly 365 days or half of that. That is very, very common, and most likely also some instrumental effect. For instance, the annual shift of the spectrum on the detector due to the barycentric correction, and other effects that have annual periods. So anything related to 1 day, 1 year, and also even sometimes to 1 month, because if you are scheduled on a telescope that also has a dog type instrument, the sampling may also have a monthly repetition rate that can also be suspicious.
Yeah.
Yeah,
and,
absolutely.
Okay, so maybe one last thing before handing the floor to Heather, is that the aliasing does not create signals. It's like, if you have signal somewhere, then you will have signal at the alias, but I mean, you will not have power at 1 day just because there is an alias at 1 day. You have to have low frequency signals so that you have an alias at 1 day.
All right, and then the next thing that we're going to walk you through here is really just kind of a sanity check for your fit. So if you've been following along and been clicking when Nathan is clicking, then you might want to know if you've done a good job, or if you somehow clicked somewhere you weren't supposed to click. And Nathan kind of alluded to it already by phase folding his data. So by going up to that time series, and if we click on phase fold, then we fold on the orbital period, and you can see if we have a really nice fit where our model is explaining the data. So this is kind of what you would hope it looks like. And if you wanted to try and replicate exactly what was in the Nobel Prize winning paper, you can go back to that data selection and select only the original data set, and then you should be able to see that it looks exactly like what they have in the Nature paper. The other things that you might want to look at for your sanity check here is go ahead and say, we can look at the period and the semi-amplitude. So Chad mentioned, and it was mentioned a few other times, that what the semi-amplitude is here is that sort of half amplitude that you see. And for this one, we have 56 meters per second in an orbital period around 4.23 days. So if you go to your favorite database and double check those, or you could go back to the Nature paper, but an excellent one here is this exoplanet.eu, or you could go to the NASA archive as well, or use the DACE one to query both of them. But go ahead and you can check and see and be like, yep, we did go ahead and we matched bang on pretty close to what we would expect. Of course, you're not always going to be able to have that sanity check if you're not repeating something that's already done in the literature. For that, then you probably are going to want to use an MCMC to sort of look at the potential correlations between your parameters and to quantify the uncertainties in your data. That's a little bit in depth for going over live with you here, but Nathan has put together one of the tutorials. Is it in part 3, Nathan? Oh, you're muted, Nathan.
Yeah, no, the MCMC is not in any of the tutorials, but it's in the procedure to follow it in the cheat sheet.
Yes, that's it. So it's in the cheat sheet. So we'll go. So that brings us naturally to where we find the cheat sheet. So you'll find that from the main Sagan workshop webpage, and then you go ahead and you can click on it there. You should be able to find it through the sort of various tutorials. So Nathan has shown you, if you go straight from DACE website, you can find it by clicking on the tutorials as well. And then you scroll down to the radial velocities. And Nathan has done a great job of going through here and putting circles around all the things that you want to make sure that you can find, all those boxes. So if you don't remember how to load up the radial velocities, where you found those, or how you export a plot or something, you can come to this cheat sheet and check it out. And that will also walk you through how to do the MCMC. So for that, you will have to download another program, but it's not the spleef thing that people have had trouble with. And so in theory, everything should run smoothly, and you should be able to follow the steps through there. And then if you have questions on that specifically, you can pop them in the Slack channel, and we can try and help you, guide you through that.
We are planning on going through the MCMC maybe in Wednesday. So by then, it would be nice if you could download the Java runtime and the environment that you will need, and you have the link there to download it. And then it's like a roughly 10-step process that we'll go through later on.
Yeah, but in terms of like knowing the basics for fitting your planets, we don't need the MCMC. We can just use the DACE platform as is to go ahead and do most of that, but the MCMC is nice for getting a good handle on your uncertainties. And when Nathan and I chatted earlier today, he made a very good point that basically in the year of 2020, if you don't have an MCMC and you're publishing a planet detection, something has gone probably pretty wrong, and you may not be believed. So they're quite common. It's a very useful tool for getting a handle on your uncertainties. One other thing that we didn't mention is we can also bin the data by different things. I did see at some point in the chat that someone, I think, had a little bit of trouble loading some of the data perhaps. And so if you get to a point where you have a lot of data and it's slowing down your computer because it's a lot to transfer, you can look at various binning sections. Like you can do nightly binning, for example. And you do that with the data selection, is that right, Nathan? If nightly binning is available for that data set, you would see it. Yeah. And you can do a custom binning there.
And then don't forget to click on apply data selection, otherwise it will not be taken into account.
Nathan, can you elaborate on how the false alarm probability calculation is done? What's the engine behind that?
Okay, it's an analytical formula that I derived with my colleague Jean-Baptiste Delille. Well, I think actually in that case it's Baluef's formula, but basically you have a theoretical framework to compute the FAP, which is the extreme values of stochastic processes, and it gives you an analytical approximation of the FAP, actually depending on the maximum of the parallelogram and of the frequency range that you are looking at. And this analytical formula is validated with simulations. So we have tried several types of sampling, and you simulate millions of periodograms, and you check that the distribution of maxima of periodogram matches your analytical formula for the FAP. And it's very and the highest the peak is, like the more significant it is, the best is the approximation. And I've never found a situation basically where you would want to publish a planet, but you are not sure because your approximation is not valid.
And Nathan, do you have a reference for that? Because if so, we could add it to the Slack channel later when we're offline. Oh, it's just there at the bottom of the page as well?
Like here, the analytical value is from Baluef 2008. But in the DACE notebooks, where you can take into account the correlated noise, then the FAP is given by the formula of Delille et al. 2020. I will put both references. So yeah, well, if you use DACE, you might want to look at this information so that you know which papers to cite appropriately.
One other question that I've seen a couple of times come up, and maybe we're going to get into this in the later days, but is it possible to use DACE to fit both RV and photometric data simultaneously?
Not at the moment, but maybe in a few months.
Okay.
It's been in discussion for quite a while.
And one thing that you probably could do is if you're using a Jupyter notebook or something, you can still be using the data that is hosted on DACE for the photometry and the RVs, and still use the various tools and APIs that are available, but you would then just have to stitch them together and how you fit them together if you want to do it simultaneous. So you could probably do a bit of a workaround if you wanted.
Okay, one more open question here. Could you discuss the benefit of binning versus losing some of the signal information in your data?
Yes, when you have correlated noise within your night, binning is a cheap way to account for it. Like when you have correlated noise of half a day, or like of a correlation time of half a day or so, it will account for it. Like it's not an optimal treatment of the correlated noise, but instead of going on, instead of using a complicated correlated Gaussian noise with parameters and which makes you invert matrices a lot, and it makes your algorithm very computationally intense. Then you just bin the data and it will give you a reasonable guess of what you should do with the correlated noise. But if you had correlated noise on longer timescales or with very peculiar patterns, then that would not be optimal, I guess. I discussed it in a paper about eccentricity. If you don't take into account the correlated noise, you might have spurious eccentricities, like you might see planets appear at eccentricity 0.6 while they are compatible with 0.
And just one thing to add here in that has been brought up is that, so this is just one tool that is of the various suites of public tools that are available. Another one is ExoFast 2. And that is a tool that is available publicly that you can download online and use. And it uses, and you can do simultaneously photometry and radial velocities with that.
Yeah.
And it's written natively in IDL, which is one of the reasons why we chose to go with the DACE platform, is because the Python is open source, so everyone can use it for free. And just because there's a lot of nice tutorials, but it doesn't mean that it's the holy grail by any means. It's just a useful tool. So go ahead and check out ExoFast 2 as well.
In the fourth tutorial on DACE, there are a couple of references to other softwares that you can use. Also for Bayesian computations, and but also ExoFast, and you will have the links to download each of these softwares.
Any other questions?
There's a question about where do the priors come from for computing false alarm probabilities? What assumptions go into that?
So basically, when you are computing a periodogram, you are comparing a base model to this model plus a sinusoidal function. So here the base model is just the offsets plus the white noise, which follows the nominal error bars. And also, yeah, something we didn't mention is that in DACE, by default, some instruments have an extra value, have an extra jitter that you can also fit if you click on the fit box. So assuming these values for the noise, assuming that you have only these linear predictors, then your question is, how often would I have a peak which is at least as high as the one in the periodogram? So basically, if my data was pure noise, how often would I have a peak at least as big as this one? And the value here, 10 to the minus 6, means that it would happen in less than once in a million case, like maybe once in 5 million cases. Something like this.
Okay, thank you.
Yeah. But you don't have a notion of prior as you would have in a Bayesian analysis, for example, right. which is one of the advantages for some, but which is dangerous in some ways also.
Yeah.
So one question I saw come up just now is it possible to identify pulsations in the data if you would upload your own? And yes, in the sense that pulsations are, so I'll talk more on Wednesday about the origin for those, but if you're talking about things that are periodic, which if you have pressure mode oscillations, for example, those are periodic, so they'll show up in a periodogram. So you can go ahead and use this as one particular tool to look for those and to identify them, and you should be able to possibly see them by eye as well, especially if you're phase folding on the period as well. But I think we've come up to the 45 minutes, so I believe that's the rest of our time. So
yep.
Hopefully everyone should have found their Nobel Prize winning planet and have the basics down for how to find planets in DACE. And again, if you have other questions, feel free to use the Slack channel. And but real quick, Nathan has a good point. We'll show you just very quickly how to load the mystery data. So you have various mystery targets listed as Sagan_system1. And there are 5 of them, right, Nathan?
Yep.
Yeah, so you would either do Sagan_system1 or 2 or 3 or 4 or 5.
Okay, so this is weird looking, and if you want to have it to a more classical display, just click on the fit button and then you can remove the outliers as you've seen in that tutorial.
Yes, so hopefully you should be able to have a play on your own and see if you can fit one of these. You can already have a stab at these various mystery targets if you want, or you can take your 51 peg example, or say you have another planet that is your favorite example. You can see if it's on there and you can go ahead and have a play and with the various different functions and go ahead and check out Nathan's tutorials as well as keep an eye on that cheat sheet.